Right, it's also possible to analyze these two-dimensional collisions with Tracker. And so this is a video of a collision that was taken from above. These collisions kind of have to be on an air table or an air hockey table because it needs to be sliding, so there's no rotational energy involved, and it also needs to be low friction so that we don't have any outside forces for the conservation of momentum to hold. Okay, so anyway, this video was shot at 30 frames per second, so I'll just double check that, 30 frames per second. In fact, I might just make this a bit bigger. Also, it's 80 or so frames, I think. Let's have a look. 89. So I don't want to analyze every single frame. I'll go every second frame. Okay, and then I'm going to create a point mass for this little thing. I'll call that mass A, and I'll define this mass. Now I measured the mass of this puck beforehand to be 27 grams, so it's 0.027. And then I'm going to create mass B, and mass B I measured to be 54. Oops, there needs to be a decimal point there. Okay, and then I also measured the big puck to be 8 centimeters in diameter, so I'll set that here. That's 0.08. Okay, and then I might just set my coordinate axes somehow. I'm just going to put them here so that I know where they are. I can move them around later and all the data will be changed. Okay, so then I'm going to track these objects. So I'll start with mass A, and I'll track the center of mass A. So the student there was holding it in place so that it didn't move too much before the big puck came. And because the frictionless table, even on even the slightest little lean, that things won't stay in place. Okay, you can see here that the frames are getting a little bit blurred, and that's because it's shot at only 30 frames per second. So now I've tracked that basically until it's left the screen. Now I'm going to go back and I'm going to track mass B, and to do that I need to first find where it starts to come into shot, which is there, and then I'll track that one. Okay, so now we have tracks for the two objects in question. We can just watch that unfold. Okay, and now we can use that to analyze a few things. The first kind of cool thing that we can do is to watch the motion of the center of mass. If we include these two masses, it'll create a new track for the center of mass of these two, taking into account the fact that the masses each have a different mass. So you can see that the green track there is the center of mass. So if I make these really long, in fact all steps, now you can see all those green points there are the center of mass, and we can see that that's in a more or less straight line, and the points are pretty much evenly spaced. So it's a constant speed in a constant direction. So the center of mass, because there are no external forces, maintains a constant velocity, which is one of the ideas they need to get their head around in year 13 NCEA or level 3 NCEA. Okay. The other thing that we can do is have a look at what's going on with the momentum. So I'm going to focus now on these graphs. So I'll create another graph here. So this is going to be mass. Oh, in fact, while it's here, I might just quickly have a look at the center of mass. So we'll look at velocity magnitude, and it might look like it's varying a lot here, but in fact it's maintaining a pretty constant velocity of around 0.17 meters per second. It stays kind of within 200ths of a meter per second of that. And the reason it looked so wonky at the start is because this by default always zooms in on the data and adjusts the axes so that the data takes up as much of the graph as possible. Okay, the second thing that we can analyze with this, and I've had students do this. Why can I not access it? Let's see. I've had students do this in a structured way on their own over a period in a computer lab. So if we change this to be mass A and we change this to be mass B, and we look at the x momentum of mass A and the x momentum of mass B, and in fact I might just add another one here. Of the center of mass. Once again, it's a little bit deceptive in how it does this. Okay, so we can see that this center of mass is actually gaining a bit of momentum in the x direction, or losing a bit of momentum in the x direction. So there's a slight lean on the table probably. But if we look here, we should be able to see, can we sync these? These are confusing because they're starting at different points. So if we change this time to time equals 0, and now they both start and end at the same point. So here the momentum of the smaller of the pucks remained 0. It started wiggling a little bit here. This is where the student released it. So it was moving a little bit between those points. And this is the point where at about 1.7 seconds is when we had the collision. And suddenly the red puck's x momentum increased dramatically and stayed at this higher value. At 1.7 seconds, the x momentum of the, in fact I might just put it at a little bit of an angle so we can see it more clearly. Okay, so that's probably clearer now. So the reason why the x momentum was so tiny is that the motion was practically vertical there, so there was almost no x momentum. But now we can see that here this one starts with about 4 thousandths of a kilogram meter per second and drops down to about 0.5 thousandths. The red one goes from 0 up to about 3 thousandths. So while the blue one drops by about 3 thousandths of a kilogram meter per second, the red one increases by about 3 thousandths. And we can do the same for the y momentum. In fact, I might just show that here as well. Px. So this is for the center of mass. Here we can now see that the momentum remains at about 3.5 thousandths of a kilogram meter per second, which is what we started with here, or about 4 thousandths of a meter per second, which is about what we had there to start off with. Okay. Obviously, it's possible to do a much more quantitative numerical analysis of this. We can do the same with a y velocity, y momentum, which looks like this. Very similar. The red one starts off with nothing and ends up with 6.5 thousandths, whereas the blue one starts off with about 13 thousandths and drops down to about 6.5 thousandths. And so the total momentum in the y direction also remains constant. And so the momentum in this collision is conserved. Almost. You can kind of see here that if we look at the total momentum of the center of mass, it does ever so slightly decrease in the course of this, which is probably due to a slight lean in the air table. Okay, cool. So that's you can do a much more in-depth analysis and probably a more convincing job of explaining it, but you can kind of see how you can. It's quite a powerful tool for analyzing these collisions as well.